Okay guys, welcome back to another video with me. We look Bernoulli's equation, which is one of the very important equation of fluid dynamics. So, linearly sometimes work done on an unit volume of fluid where the surrounding fluid is equal to the sum of the changes in kinetic and potential energies per unit volume that occur during the fluid flow. So I'm English, but the statement basically the option I'm using change below work done, yeah. Lo moving on the volume of fluid and by equal lo sum below change below kinetic na potential energy. Time you add in changes below all and by equal lo slow work done, yeah. Change below slow work done. We need to move him one plus fluid element kind of thing, or volume of fluid from one point to another. So the Bernoulli equation, yeah. Mostly you say representing one times la diagram, yeah. And then elevating on the pipe go height. On the height kind of same. And now you say talking sla you say studying Bernoulli lo good or explaining good lo this la diagram. So this line cross sectional area 1, cross sectional area 2. At the same time, this line V1 velocity 1 na on the line V2 and go out low and the speed velocity 2. And what I move. So what I move inside. Yeah, kind of. Now suppose me elevating to the height one plane lo here lo point 1, we can toss him slam H1, slam H2. Height here. Okay, now suppose me put him on the Bowden gauge pressure meter here, then this becomes pressure 1. Now suppose me put in here, then this becomes P2 and pressure 2 by me reading law. Inside then what I move, now same time you got height, so you got him potential energy to involve in motion and kinetic energy involved. Now, low-side expression you can toss in difference in work done and by equal law difference in kinetic energy plus difference in potential energy. And by me can toss in law mathematical expression or equation which la Bernoulli statement there. Okay, now you finding work done. So work done basically anytime you move one body or mass one distance to a particular point at a given distance. Suppose you moving this body one time one given force, then product produce la force times distance and basically work done. Yeah? So suppose you move na or if you want force lo move one body lo one point colonel per point, then that basically you are doing a work done. Or that force is doing a work done. Remember, this is linear. Suppose me start law angle, then you can put him force times distance times cos theta. But this one is linear. So we considering linear motion. The work done. So this is the equation. So you can thousand delta work done is equals to work done 1 minus work done 2. Now you by asking, you mean that of change in work done or change in kinetic energy or change in velocity or whatever you mean that of final minus initial, but you mean talk 1 minus 2 or initial minus work done 2. So basically what it means is that you mean need him plenty work done low, position this la wara quanta low, this la electric cross sectional area low upside there. Therefore, you need him plenty work done, so work done by me remain positive. Now, this la minus basically mean same you got him reduce work done low upside. You don't need him plenty work done. Low you need him plenty. So you mean lose same work done 1 minus work done 2 or initial minus final kind of thing. So now you can replace him this law W one time equation by me, which is force times distance 1 minus force 2 times distance 2. Now suppose we can think in this equation pressure equals to force on area or force is equals to pressure times area. Okay, it's like equation now. We can instead of force we put in this in place lo point 1 and point 2, so we can toss him P1 A1 D1 remains minus P2 A2 D2. Slam delta work done, yeah? Change in work done. Now, if we can think in the same, we can look at the area times distance, and it's basically a volume. So suppose we want a cross-sectional column of water here. So we can do same. This is the column of water. And we got him area cross-sectional. And then we got him distance. Move fluid distance, let's say per second. Then what will happen is it's like area times it's like distance is basically volume. Because same this like meter squared, this like meter. So in terms of SI unit, this is cubic meter, which is equals to volume. In a cube or something, you can say length times width times height, kind of same. So we talk suppose we got in narbla volume body, we set of same length times width times height, and mostly we set over. So this is area, and that is height. So area times height as well and volume. But in this case, our area is the cross-sectional area times the distance, which is basically just the height in this case, then it gives us the volume. Yeah. So we can do same. This is just volume, yeah. So we can do we replace him this la volume one time A1 D1 we replace him with the volume. So I become P1 V1 minus P2 V2. So this is delta work done. Best part of the equation, yeah. Now we call the second part and kinetic. So kinetic energy is given as half mv squared. M half of the mass times the speed of the object, or in this case the fluid. So now we can talk change in kinetic energy now and final kinetic minus initial kinetic. Sorry, 1. So it becomes half mv 2 squared minus half m1 squared. So this is the form of the kinetic energy for this part here. Now, we have same mechanisms like equation density equals to mass on volume. Mass is equals to density times volume. Equation. So in terms of m, or instead of m, we can replace him one time density in volume. So we can talk half density or rho v volume 2 and speed 2 squared minus half rho volume 1 speed 1 squared or velocity 1 squared. This is delta k. So this is your second part of the equation, delta k. Now you may find him delta u, or potential energy. Remember, this is gravitational potential energy. We got him to play, we got him elastic potential energy and gravitational potential energy. This is the gravitational potential energy. mgh in slam. Gravitational potential energy. So delta U, you can say U2 or final minus U1 or initial, which is basically M2GH2 minus M1GH1. Now suppose we replace one time this equation, we can talk rho volume 2 GH2 minus rho volume 1 GH1. That's delta U. And delta U beli me. Okay, now ini bunyi more kita akan mapping Bernoulli equation. So delta W or work done is equals to delta K plus delta potential. So delta work done beli me and P1 V1 minus P2 volume 2 is equals to delta K and half rho volume 2 speed 2 or velocity 2 minus half rho volume 1 plus T1 squared plus the potential energy M rho volume 2 G H2 minus rho volume 1 G H1. So suppose me look and this line basically come up in M o'clock come up with same Bernoulli's equation now. Suppose you look good. So la volume suppose me to same this is the volume when we talk V is equals to area times distance, which is basically meter cube in terms of unit. Then suppose divided by t, suppose this level move low sampler time, let's say 1 seconds, then this becomes cubic meters per second, which is basically your volume flow rate, which is V on t, which is basically meter cube per second. And basically MQ here, continue the equation to Q1 is equal to Q2, meaning flow rate go inside layer and by 1 current time flow rate go up. Now you can do some volume per second in every column of the water going up and by same zone. The volume per second, and which is basically the flow rate and by same. So therefore you can talk V1 equals to V2. Now you can also get the volume here, you divide them on. So V lawyer V let's get the volume. When we remove all the volume now, and by because I'm constant, then by me talk P1 minus P2 is equals to half rho speed or velocity squared 2 minus half rho velocity 1 squared plus rho GH2 minus rho GH1. Now is the Bernoulli equation. Now me rearrange it now. Okay, the minus blow 0.1 go upside. Now plus blow pressure 2 here. Minus blow pressure 2 come upside number plus. So P1 plus half rho V1 squared plus rho GH1 is equals to 2 plus half rho V2 squared plus rho GH2. Now this is our Bernoulli's equation. Bernoulli equation here. So the diagram is minimum same. Suppose water and flow slow here, then pressure back one tap. And suppose water and speed low upside, then pressure back come down. So low go back low continuity equation where Q1 is equals to Q2 and by A1 V1 equals to area 2 speed 2 or velocity 2. So low continuity equation and minimum in order for it to be valid, because now you may have them different area, cross-sectional area, area 1, area 2. Area 2 is smaller than area 1. So you can talk, suppose area 1 is bigger, then its velocity should be reduced, or meaning that water m flow slow. Suppose area 2 m come down, then means speed low 0.2 must increase. So means you got big area here, water by flow slow low pipe. Now suppose you got lick area here, water by speed. One can low. When I garden hose, suppose you holding finger below eye blow hose, they reduce in size blow cross sectional area low water go at by speed Now you lose again and go slow now water by drop go down. So in terms of continuity equation, the greater the area, velocity by come down. The lesser the area, velocity by go on top. Lo Bernoulli's too. In terms of Bernoulli, remember, time water move slow, pressure by go on top. The time water move fast, pressure by come down. So, Bernoulli equation. So, Yam tasol ipla need simple more help or side blow explanation or any topics of physics. Ipla can request or ipla comments. You can just subscribe to so like. Yam tasol. Thank you.